So please welcome Jeff. He's going to talk to us about petabytes of data, how to use R at scale.
Hello, my name is Jeff. This is a microphone that's not made for Lemmy. I am a machine learning field engineer for Cloudera. You would think I would know more about agriculture, given my job title, but I actually don't. Field is the term that American companies like to use for customers, so I'm generally focused on helping customers build out machine learning applications. Today, if you're an R practitioner and you want to know how to access a Hadoop cluster and understand the petabytes of data that are going through the system, I'm going to talk to you a little bit about that. So, agenda, I want to focus on the problem we're solving specifically, talk about how it's solved outside of the world of R, talk a bit about the components that go inside, how this works and interacts with R, some useful things to know, things I would have liked to have known when I started down this particular journey, and some links to get you started. So, when I first started getting learning data science, I did the Johns Hopkins data science course on Coursera, and you have to learn R, and I'd never used any R before, and R is actually quite cool. It's kind of like command line Excel. So I got my head around R, but at the same time I was working at an internet service provider, and our job, we were analyzing huge amounts of data that was coming from NetFlow, and those two worlds don't collide and interoperate particularly well. Like you hit about a 2 gig limit on R in my experience. I know this might be a 32-bit, 64-bit problem, but I couldn't seem to get it to run in 64-bit properly. And anytime I tried to work on something bigger than 2 gig concurrently, I would hit some kind of ceiling. So I understand that there is a problem from a scale perspective where you have one MacBook that you're trying to run your code against and it doesn't operate effectively. The other one though, and I think if you are in the data science field, and this is quite important, is that for a business, so I work with pretty much all the big telcos. I work with all of the big banks. I work with all of the big insurance companies. Discovery Health use software that we make, and I talk to them fairly frequently. So what's important is that they want to have the ability to do machine learning better. And machine learning algorithms work better when you give them more data. So that is an advantage from a profitability perspective. And as a data scientist, you're going to get pressure to be able to have to utilize this much larger data set. So you need to know the techniques that you can apply what you've learned in the world of R, but to the data that sits at scale. So how is this solved outside of the world of R? We have Google to thank for the Google file system and MapReduce. There's a guy called Jeffrey Dean. Go read up about him. He's an interesting dude. And they created the technology that became Hadoop, that becomes the stack that is pretty much the standard that is utilized by most of the stuff. So when we're talking about the big data stack, we're talking about Hadoop. Ooh, what happened there? Okay. Now the Hadoop stack specifically is based on HDFS at the bottom. HDFS is a file system. It's kind of an infinitely scalable, I pressed the wrong button. That was me. Okay. HDFS is the infinitely scalable file system that you use. You have a resource manager that sits on top of that. That's called Yarn. And it allocates services that are going to go and run against those nodes in the cluster. MapReduce was the first version of being able to run against a very, very large data set. MapReduce uses Java. It's archaic. It's weird to use. Most people don't use it anymore, and we've replaced it with Hive. And Hive is how you do your SQL queries when you want to run against this world. I know I'm going very quickly. This is not really the focus of what we have. I can talk about this stuff for hours, but Hadoop, good. So Hadoop and MapReduce didn't solve a particular problem well. So the group of people who understand these things got together and they created something called Apache Spark. Apache Spark is an in-memory data processing system that can run at scale in a cluster against this very, very large data set. And what makes it different is that Apache Spark is a first-class citizen in the Hadoop world. It uses Yarn, it uses all of those processes. But what you do fundamentally with R in terms of your data processing, Spark is the place that you will do that same thing, but you're going to do it at scale. So Spark is how you're going to process against a petabyte of data. So how does Spark work? Spark starts with a client program. This client program instantiates. It goes and says, talks to the cluster to say, I need some resources. Your data exists inside the cluster. Please give me access to that data. And your Spark job is going to go and say, I'm going to serialize this data. I'm going to work in the cluster, and I'm going to work in a distributed way against this petabytes of data. So the standard default unit of data storage in the Spark world is something called a resilient distributed data set, and that's how Spark understands data. So what we're doing is we have, let's say I've got a CSV file that's 200 terabytes big, and I want to do processing against that. Spark takes that, it goes to the cluster and say, node number 1, pull a bunch of data into memory, pull the first, say, 20 gig into memory. Node number 2, you do the same. Node number 3, you do the same. And it builds an in-memory picture of that data set for you to do your operations against this. And using my brilliant data visualization skills, I have represented that particular thing using this view. So when we do normal data representation in the early versions of Spark, it was just a data set. It knew that that data existed there. It didn't understand the structure of the data. But with the newer versions of Spark, we know that actually unstructured data is not as common as people think. There's a lot of it, but it doesn't get used as much as people like to think about. So we apply structure to that data. So there is a move from an RDD to something called a data frame, and what your Spark cluster is doing is holding in memory something that has rows, columns, it has type affinity for different columns. We can do a bunch of things with those columns in memory with those data sets, and effectively it's a table, but it's a table that's 200 terabytes or a petabyte big. So we can do standard operations that you would do in R. So when you're doing something in R, let's say I have a column and I want to divide that column. It's a numeric column and I want to divide it by 10. In the world of Spark, we call that a map. And what we're doing is we take that column, but at a Spark level, I'm creating a new RDD. I'm occupying some new memory and I'm reducing that particular column by an amount. And if I want to filter, I map to a new column, but I keep everything on the same node. I don't move it off to a different node. And I would say remove that because I'm doing a filter. So I just basically create a pointer to an empty space. What's important with Spark is that everything is now staying on one server. It hasn't moved. All of that data is in memory on that one particular node. But if you do something that is a group by, it becomes a shuffle, it starts to need to move the data. This is computationally expensive, so this is one of the things that you try and think about when you're starting to deploy Spark-based applications, is that at a point it needs to move data around, so that's going to cost you a lot in terms of the way the Spark process works. Concurrently, because we have a big cluster of thousands of nodes, we can do lots of these at the same time. And as I pull all of these representations into memory, I have two tables in memory. I can do a join. So now we can start to shuffle. We can do all of the things that you would normally be doing on R on your local machine. We're just doing them at scale. And you're never really going to look at 200 terabytes of data. So I want to take a small chunk, and that's a little bit of information that I want to be able to use. Now, the way Spark looks at this is to say, all operations that stay on a node, I'm going to cascade those together, and it calls it a stage. So it will group those operations. So on node 1, it's going to run the map, then the filter. Node 2 is going to run the map and the filter, and it's going to manage those jobs in one cohesive clump called a stage. But when you need to do something that's going to move data around, it's going to create a new stage for that. So it creates another stage boundary. Concurrently, I'm doing that on another data set on the cluster, so I have another set of stages, and Spark is managing all of this running concurrently. Now, what Spark does is it does standard data operations, and it has a lot of this capability, but in order to make it more useful, we want to add more libraries to Spark. So Spark comes with a whole bunch of other useful utilities. Because we have Spark sitting in memory, we can run we have data sets in memory. We can do SQL queries because it is a table, so we can do queries across SQL. We can kind of create these infinitely windowing tables, so it does Spark streaming, so we can create stuff that works on real-time data. The machine learning libraries sit there. Machine learning is very iterative, and one of the things that Spark is very good at is coordination between different nodes. So something like a linear regression that's doing lots of computation and creating lots of little changes in the RDD, all of those nodes are talking to each other to say this is the updated information. And then GraphX, which is a thing. I don't know what it is. I've never seen a customer use it, but for some reason it always ships with Spark. So how does this work with R? The key thing here is, and I don't actually know how to say this. I'm going to say Spark Liar, but I've heard Spark Liar. Spark Liar. Are we good? Okay. There is also Spark R. Spark R is the thing that comes with the normal Spark distribution, but Spark Liar is significantly better. As a person who advises customers, I say, look at this particular implementation. It covers more of the libraries. It does more things, and it's a lot more useful. And how this operates differently to standard Spark is your client program is R. So R is instantiating on your node that you're running. You load the Spark library, it talks to the local Java subsystem and creates a little Spark driver on the place where you're actually running R. It then will talk to the cluster for you. It will do all of the management of the data transfer. This is an important thing. You are then instantiating something. The code you're writing on your local R client is executing on the cluster separately. One key differentiator is each of the nodes in the cluster needs to have R installed because it spins up and brings up an R instance with it. And as that instance is running, your R process is making sure that your data is managed from an R perspective. So the dplyr type implementation is managed through the R system that's running on that node. If you want to run a very specific bit of R code, some kind of mapping process that you're doing something that isn't supported in the Spark libraries, there's something called a user-defined function. And as it goes through each line of code on the row, or each line in the row, it's going to send that from the Spark process to the R process it, and then send it back. It's incredibly inefficient and very slow, which is why we never advise people to do that. However, we have Apache Arrow, and it's the newest version, for the latest version of Spark and the latest version of Spark Lyre. It creates a point in memory where both your Spark process and your R process are accessing that. And Arrow is very good and very efficient. So now we can get similar types of speeds as to what those fabled Scala programmers are doing when they're running their Apache programs. Okay, useful things to know. This is stuff that you kind of learn the hard way when you're first starting with this. Spark does something called lazy evaluation. And lazy evaluation means that it is going to look at the whole set of sequence that you want to run, all of the bits and pieces before it executes. And this is done because if I've got a filter that says I only want to do this on numbers smaller than 10, it will go back and push that filter earlier in the pipe so that it doesn't work on too much data and doesn't overtax the system. Where I see people often getting caught is, especially if you're using interactive code, you've hit enter a couple of times and you suddenly then try and pull a little bit of data. When you pull that data, all of that executes. You have made the assumption that all of those processes have happened along the way, but they actually haven't. And things get very slow or things might break. The other one is that the driver programs, that little end piece that you're running, most people, if you're working on R, you have this kind of almost muscle memory of just looking at a little bit of your data. You'll grab a piece to say, what is my data doing? Especially if you're doing data discovery and exploration. When you're doing that in Spark and you accidentally select everything and you try and pull that down, that's 100 terabytes that's going over your network. You're going to get an out-of-memory error. And of course you're going to moan at the vendor. You're going to say, this is definitely something wrong with your software. And because I'm in sales, I'm going to very nicely point out that perhaps you're overloading your driver. You did a take of 100 terabytes and your computer is actually quite small. But that's because I'm in sales and that's how we close business. There is also group by key. Now, this is a standard thing that you would do from a Spark programming perspective because it doesn't have any performance hit. Group by key is not something you should be doing if you are running this in Spark because it then pushes all of the data to the end and then does the shuffle. There's something called reduce by key, which does it on the driver end. So it actually, well, not on the driver end, on the executor end, it actually manages a little bit better before it gets shuffled all the way through. And then data skew. When Spark decides to actually break things up and starts to take the data and starts to parallelize it across different things, it takes a key. It chooses one of the fields to say, this is the key how I'm going to break that data up. Sometimes if you don't have a key or you have the same key across all of your data, your parallelism doesn't work and you get data skew. You end up with this one particular node that has all of the data and all of your other nodes are running quite a very, very small amount. So you'll see that it takes a long time to actually finish that process, but ultimately it's a data skew problem. And the question you ask is, how do I find out if I have data skew? You use your Spark UI. This is the most useful tool if you are a data scientist and you're working against a cluster, because the cluster will provide you all of that information that you need. So you have the ability to go there and also work with your data engineering team. These are the people who should know how this stuff works. They should be able to look at the Spark UI and tell you that you have data skew or tell you that you have these particular problems. It also shows you the DAG. So the directed acyclic graph, if you want to sound cool, is the view of the stages and boundaries that happen between the way Spark executes. So when it makes the decision, when the optimizer decides, how am I going to put all of the stuff together, it will build this graph for you and it will show it to you so you can understand where things are moving. If you don't ever want to do things programmatically, if your view is that I only ever want to do something that looks like a SQL query We also have something called implier. Implier. It is a dplyr set of verbs to run against a large MPP database. Our MPP database in this instance is called Impala, but it just reduces the complexity from your perspective. You can't do machine learning with this. You can't do a lot of the other optimizations like streaming, but it is available and it makes life a little bit easier. So in terms of getting started, I'm fairly sure these slides will be shared. So there's a list of links that you can go to and go and have a look to see how all the stuff works. And with that, I give you back 5 minutes to your day.
Thank you.